Well, my job is to fantasize and give you the story of the transformation of what we learned from these experiments into the forecast model problem. Okay. So I'm going to give you a timeline related to Fife. I can't see anything, but never mind. A timeline related to Boreas, and talk about ongoing model development and bring you up to date in my world of how this whole strand of research has been connected together into the present. But the timeline starts like this. I was not funded by Fife. I wasn't involved in any of the planning, but I got a phone call sometime during the early part of the Fife experiment from Bob Grossman. It was the classic, "We need your help." And I won't tell you, since we're being recorded, exactly what he said about why he needed my help. But he needed my help to try and explain and understand and interpret the boundary layer part of the problem. I lost one of my microphones. I can tell that. So I flew out to Manhattan, Kansas. Poor battery, perhaps. But I'll continue anyway. Can you hear me? This is the microphone. It's not this recording one, yes? I'm not sure. And I spent a few years mostly working on the aircraft flux data from the Twin Otter and from the King Air, and doing surface budgets. But I also realized that this was an immense opportunity with 10 PAM stations and a dozen to 20 flux stations scattered over this small area to attempt to produce a data set that was suitable for evaluating models. And I knew that was a critical issue because I knew how bad they were. I'm back online, I see. Momentarily, I'm offline again. So we created this mean time series, and I'll discuss that in the next slide. And what happened then was that fortunately became available at just the time the European Centre Model was trying seriously to replace their rather primitive land surface soil model with something that represented the timescales from the daily timescale to the monthly timescale for water storage and evaporation. That went into parallel testing July 1993, which just happened to be the month of the Mississippi floods. And the results were so stunning that it was in operations by the middle of August. And that really, now I have feedback.
Yeah, that's too much. I'll figure it out.
This is my assistant. I just want you to note here that the analysis of the data here for getting through to this time series took about 5 years. It took European Centre only 2 years to go from beginning of a model into operations. Here's a list of lots of key papers, and I don't know how well you can read them, but some of them, based on the Fife data set, have close to 800 citations at this point. Just a mark of how many of the land surface models use the Fife data set for testing purposes and model development. Well, the Fife data set, I've put a picture up here of John Ball, who did a lot of the hard work. Basically, what we did was, okay, we had these 10 PAM stations. We had, depending on the time of year and which year, we had anywhere from 10 to 22 flux sites, all with many cases with different instrumentation. And I said in the paper, the biggest difficulty in generating an interannual meteorological and radiation flux time series averaged over the Fife site was cleaning up the data. And having been involved in other field projects before, I realized this wouldn't happen unless somebody sat down and did it. The data, of course, in the late 80s was much more spiky. We didn't know a lot of the bias signatures, different instrumentation. And we did what we politely, retrospectively call a multi-site ensemble. If you know what multi-model ensembles are for climate models, it's very simply, we have all these climate models and they all have different bias structures and unknown errors. We average them all together and assume that the result will be much better. We did the same for the Fife data with a lot of manual editing. just a mean and a standard deviation. I did some theoretical analysis. This primitive picture here from the old days of transparencies shows you the different diurnal cycle. I'm just falling apart.
We all are.
Is that all? It may or may not work, but it's now in my back pocket. I don't know. Is this the other?
I don't know. They're tangled. There you go.
Good press.
However, wet soils, these are all dry, clear sky days, high thetery, low cloud base, and dry soils, low thetery and high cloud base. And I constructed vector models which have gone on to be very useful for understanding land-atmosphere coupling. But what really, I needed to go to England in the summer of 1992. So I took the 5 data set and I said, let's see what we can find in the way of errors in the modeling system. And I was a little horrified when in the first week I found about 5 errors, and I list the first 6 here on this particular slide. And errors that the shortwave downflux was too high, and that was simply an error in their model calculation of the clear sky fluxes. The ground flux was too high, they didn't have a skin layer, so the response of their first 7 centimeters was too slow, 10 centimeters. They had no latent heat flux in October, and we were measuring it in Fife. They had soil moisture storage errors. The skin temperature was wrong, that was a roughness, heat and momentum error issue. The diurnal cycle was out to lunch, and that was because they had no boundary layer entrainment at that point in the model. And on sequential dry days, the bound ratio rose rapidly and the temperatures drifted upwards. Again, a soil moisture storage error. But what was really transformative was at the end of the week, I went in a little bit sheepishly to Tony Hollingsworth, who is the head of research, and I said, with a deep breath, I have found 5 errors in the model this week. And his eyes lit up. He jumped up from his chair and he said, fantastic, we'll fix them, find 5 more. And that, as I will say, is one of the things that changed my life in relationship to them, because I had had experience in other countries which shall be nameless, where if I found an error in the model system, they said, oh, don't say anything about that, it might affect our funding. Okay, I've even been told you have to withdraw that critical abstract, it might affect our funding. But at the European Centre, the attitude of an institution driven by science to improve the model systematically now for decades has always been fantastic, we'll fix them. And they would. They would typically fix them in 2 years and work on the next. And I'm going to scan through some of that. What they did, and this is only part of it, was simply go from a 2-layer soil model to a 4-layer model that represented the diurnal cycle, the weekly timescales, the monthly timescales, and the quote on the left says, comparison of the results of the old model with 5 observations suggested improvements in 3 areas. And they're very, very primitive things. A mechanism to get the precipitation rapidly into the ground where it can be stored. Now the reference here is that these models took coefficients out of engineering books, say on the properties of soil for the transfer of water. Perfect lab things, utterly useless in terms of landscapes where the holes and the diffusivity of things going through mole holes and things is fast. The diffusion of water in soils is far faster when it's wet. Lots of things like that. But smart man, Pedro Viterbo, given the 5 data set for soil moisture and the evaporation, figured out what was necessary. And other things, the boundary layer, were also fixed. But they said they were fortunate. This went into parallel testing the year of July, the month of July, 1993. And they discovered immediately they'd hit pay dirt. This is the difference in the new model versus the old model. The old model basically had no precipitation in its 3-day forecast. The new model had precipitation, these values are in millimeters per day. That's 5, 6, 7, 8 inches of extra rain from this coupled model system, right in the right place for the Mississippi floods. Now, if you're in the forecast world, to go from no precipitation at 3 days to the right precipitation at 3 days for a flood event, you know you've hit pay dirt. And it wasn't just in the short-term forecasts. At the end of that month, I was looking at this, and I had known they had done some seasonal work that has showed the coupling between evaporation and precipitation. And I called up Martin Miller one day and late in the week, and I said, why don't we do the monthly forecasts for July? And he said, sure, we'll do them over the weekend. And on Monday morning, this being the European Centre, out came this result. And this is a 1-month forecast. And the only change in this global model system has been whether we had wet or dry soils at the beginning of the month. And this is the difference in precipitation. And over the same flood area of the Mississippi, the monthly average is 4 millimeters per day more. That's 6 inches of water for that month. So they realized that their model and its evaporation, precipitation, feedback, and the memory they'd now built in out to the monthly timescale was going to improve longer-term forecasts. Pay dirt again for them. So as was mentioned earlier, when we went into Boreas, they said, we will give you daily forecasts, which for them was a new step. To provide an experiment in Canada, in this case, with daily forecasts from an operational European model in 1996 was a step. But they have been integrated into this stuff ever since. A list of Boreas papers, the same kind of thing. But I want to flag for you here, Boreas played a huge role in the development of a new surface scheme for the forests and the rest of the world, for the European Centre, and has also played an important role in new hydrological models, and I'll come back to those, and is still playing a role in new snow models over high latitudes. Here the landmark result was something, as was referred to already, the impact of snow albedo errors. And this is a 5-day forecast, 850 millibars for spring, March and April, and we're looking down on them from the North Pole. And it's simply, the background here is, okay, the model for the globe was improved from the Fife data. They got the hydrology better, the evaporation better, but the model was still a primitive one. They had a fractional area of vegetation, and their vegetation was grass. Basically grass, with a single parameter for its resistance to evaporation. Well, grass doesn't do too well over the boreal forest, and one of the problems it had, not only the wrong evaporation, but it had the wrong albedo in winter, high albedo. Huge errors resulted in, this is the negative bias in a 5-day forecast, not at the surface, but up at 850 millibars. It's about 2 or 3 degrees over Canada, and as high as 5, 6, 7 over Eurasia. Huge errors. Been bugging them for years, and they still didn't realize what it was. But as a result of the Boreas, they realized that the trees, the sun at low solar elevation angles you can't see, doesn't get reflected off the snow. The albedo of the forest is much lower. In fact, we wrote a paper on the albedo of the boreal forests. Changing that in a terribly primitive way basically wiped out those errors. So that set in motion a chain of redevelopments of snow schemes under high vegetation that has gone through at least 2 iterations since then. And I'll show you the improvement in a moment. The other big effect of the combination of these experiments is that they then had the courage, essentially, to go to a full global model with 18 vegetation types, 8 tiles, including one for snow under a high vegetation, new environmental controls on canopy transpiration, and a first simple prognostic snow layer with proper equations for albedo and density, separate energy balance equations for the high and low vegetation tiles. And this was a huge step forward. And it went into their 40-year reanalysis, which proved to be the best reanalysis of that era. In fact, well, I'll come back around to that. I mean, they also fixed flux problems. This is what their primitive grassland model did for evaporation over the northern old-back spruce site, and the other two are the actual data. The green is the data, and the blue one is what the new era 40 model basically tuned to that and other Boreas sites produced, and you see it was a huge improvement. And berms carried on from Boreas, and I just want to show you when we went back and looked at the berms data over a much longer time period against the ERA 40 model, you see the bias is this is temperature from 3 sites, black spruce, jack pine, and old aspen, and ERA 40 in this case. And you can see there's very little sign of any significant temperature bias at any time, and humidity is on the right. Look deeper, there are some biases which have gone into further model generations. But to just carry you up to date here, on the upper panel there is the MODIS albedo. This is from a paper after another snow model iteration. And the middle one is the ERA 40 era type of model. This is the current version of the model, and the bias from MODIS here has been reduced in terms of the surface albedo to rather small values. Still pushing on that. And to give you a broader timeline, this development of the European Centre has gone through the 5-era model, the ERA 40 model. They added better hydrology, they added better snow, they added leaf area index and analysis from space, they added better soil models, and they're now at the thing that Fyfe and Boreas would long to see, is the issue of, can we do fully integrated carbon dioxide? And, I have one more before I get there. The other thing you have to realize that in the model development period, we've gone through a factor of 12 in horizontal resolution. We've gone from 108 kilometers down to 9 kilometers globally in the ECMWF system, and we've quadrupled the vertical resolution. And the next reanalysis that's just going into production will give us hourly quarter degree global with the current operational model. And that will be a huge step forward because we have fully resolved diurnal structure from that system. The coupled CO2 is still largely offline. The offline validation, as I highlighted that, mitigation of large-scale biases in the global CO2 analysis and forecast. The problem is that we are still unable globally to get the surface flux control on the global CO2 budget. We can measure column CO2, we can measure some of the vertical structure, we can compute the fluxes at the surface. We have still from the industrial output, we only have stuff from the past of sometimes unknown reliability. All these things are being worked on. And the context here is the European Centre is the only global operational system that has accepted responsibility for analyzing everything that can be observed from space. The active gases, the greenhouse gases, the aerosols, and moving towards a fully coupled system. They've picked all those, and I just thought I'd show you. Here's the forecast for lunchtime today of the CO2 forecast for the globe, showing the fires over and the industrial outputs from China, from us. And here's the forecast for the global methane budget for today, lunchtime. These things are working now in offline mode. They're not yet fully coupled into the full system. Pavel Kabat, in this particular paper, summarized this section of the talk much better than I can. Independent authenticity, and you can just read it. Well, this work from Fyfe and Boreas, improved models, lists all the improvements and said this has led to significant improvements of the skill of the forecast models. And for the land problem, it certainly has. But I bargained for a little more time, and I have no more idea how much time I have. But I wanted to tell you what I've been doing the last few years, because there are so many things that I'm learning now about Canada and the northern landscape, both the prairies and the boreal forest, that I did not know during Boreas. And part of the fact, well, this was another classic example. I get a call from Ray Desjardins back in I think it was 2012 in the summer, and he says, we need your help understanding the climate of the Canadian prairies. And I smiled. I get lots of these phone calls, you have to realize. And when they're from someone that I trust, I always say yes. I said, yes, but you have to access and process the Canadian prairie data for me because I couldn't do it. And this is just a contrast for you. The open data access for Fyfe and Boreas has been an enormous contribution to global science. the willingness here of Agriculture Canada to share this data set with me and allow me to share it elsewhere has also been a huge benefit. This data set is not only of superb quality, it's hourly, very little missing data, goes back to the early 1950s, and it has something that nobody else measures. Those of you who don't know, would anyone like to tell me what that is? Amazing, yeah. We don't know, do we? And we didn't know. I didn't know it existed till it arrived on my desk. And here's a summary. This is 15 stations across the prairies. Only one of them in the boreal forest at La Paz. It's hourly, conventional climate data, but they also trained their observers to record the fraction of opaque cloud in tenths by layer that you couldn't see the sun, moon, or stars through. Every hour for 60 years. And that is completely transformative because there's a baseline surface radiation station just south of Regina. You can calibrate it to shortwave and longwave cloud forcing. And the data is so good that adjacent stations have a one-to-one correlation. So we essentially end up knowing shortwave and longwave cloud forcing on climate timescales to about 10%. Changes everything because all our climatology has never known the radiation field, which drives the temperature diurnal cycle. And I want to show you that. But again, the first huge lesson, well, I'll come back to that, was the impact of snow. Wonderful data set. And here's a simple, all I've done here is take 60 years of data from 5 stations in Saskatchewan and map temperature against the date of first snow. Snow depth goes from 0 to 6 centimeters, and the temperature drops 10 Celsius in less than a week in this climatological mean. And we recover that 10 Celsius in spring as the snowpack disappears. Well, I now enjoy going around asking forecasters, how much does the temperature drop when we have snow? And the background here is that what we were trained in school was when it gets cold, it snows. Well, it has to get cold in order to snow. That is true. But we were not trained that the feedback, the reflection of the snow, high albedo snow, plus the long wave feedback, which nobody knows anything about, drive a feedback and drive you a 10 centigrade drop over high albedo surfaces, 6 centigrade over forested surfaces. And the result is, if you just, all I've done in these two, this is 2 stations in Alberta, and I've simply, the black line is conventional climate, getting cold in winter, 0 is there. I've simply separated the 60 years of the climate into the days with snow on the surface and without snow on the surface. In Alberta, the snow is often transient, and you see 2 climatologies, the red, no snow, and the blue with snow. And they're separated by 10 centigrade again. 2 non-overlapping climatologies with and without snow over non-forested, largely terrain. And this is what you get across the prairies. 2 separate climate. And the snow is a climate switch between those 2 climatologies. And it's so powerful that if you ask the question, if you just plot mean temperature in cold season against fraction of days with snow cover, whoosh, 80% of the variance is explained just by the fraction of the days with snow cover. And the slope of that line is even more than 10 centigrade. It's 14.5, meaning that the larger scale feedbacks between snowy winters and non-snowy winters give you more amplification. And that's a climate change signal. If we have 10% fewer days with snow, the winters will be, on the prairies, will be 1.5 degrees warmer. And we're now, of course, seeing that in Vermont, and understanding it makes things so much easier. We had a snowless winter last year, and sure enough, it was 6 centigrade warmer. How about the cloud aspect? What does the cloud give? Something also very, very powerful. I just want to show this top left curve here. My pointer doesn't work, like a few things here. These are 2 stations. One's Regina and one is Moose Jaw, and they're about 3 kilometers apart. 40 years of data, daily means of 24 values, and it's a 1-to-1 line, and the R squared is about 0.88. A little further away, a little further away. You see a drop in correlation, but you do not see bias, meaning that these trained observers, with I only found one exception on the prairies, appear to have produced an unbiased value of the short and long wave cloud forcing, calibrated. So I can then use that to stratify. January and July, and they're stratified by this opaque cloud fraction. July, you all understand. This is cloudy. That is 95% cloudy, 5% cloudy. Minimum doesn't change much. Maximum goes up. A shortwave cloud forcing dominated regime. Afternoon temperatures go up when it isn't cloudy. No surprise. The one above is the January equivalent. It's warm when it's cloudy. Temperatures drop when it's not. And the minimums become largest in spring, in the sunrise. If you look at the transition months that have both, you see both signatures. There are two non-overlapping climatologies, one shortwave cloud forcing, unstable boundary layer day, one long-wave cloud forcing, cools when it's clear, a stable boundary layer. And in the year as a whole, there are only those two climatologies, the winter one, the transition ones, and all the others look the same. And they are all statistically structured exactly the same. Once the snow is gone, the April without snow is the same as July and August. So, briefly summarize, snow is a climate switch. Prairies, grasslands, different. And the snow transforms the surface boundary layer coupling. In retrospect, it's obvious, but I did not know that until I had this cloud data and this long-term records. And to end this brief section, what this means for hydrometeorology is that we've traditionally tried to do it with precipitation and temperature. But when you look at the structure and you've got the radiation as the clouds and you've got good humidity data, you find it's a fully coupled system. And on the daily time scale and the monthly time scale, you find the dominant signal in temperature is radiation driven, cloud-driven, and the dominant coupling of precipitation is to mixing ratio. And so you've got a different separation of processes. And the data is so good that you can go back and you can see memory for as long as 5 months in the precipitation. I'll just show you an example of that. This is the climatology in April going back mapped against monthly cloud, monthly precipitation, and precipitation going all the way back to freeze up in November. And these are the regression coefficients, the normalized regression coefficients. And just look for, this is the afternoon cloud base. These values are large, all of these, and significant all the way back to freeze up of the groundwater in November and the snow through the winter. Oh, space has almost arrived. Let's see if I can get... Did I wave and Google listened? It's probably going to happen every half an hour. That's probably my time signal. And this is parallel one for July. We find in the summer that you can see the memory in the moisture variables primarily all the way back to the beginning of melt in March. But I'm coming to an end. Oh, there's one other thing that this data, because we've got a quantitative radiative measure of clouds, we can map the relationship between anomalies of the cloud, opaque cloud, and the climate itself, means of temperature, means of humidity, and the diurnal temperature range. And that, I think, will be extremely powerful because it shows us that strong coupling to diurnal range, we knew that, but as temperature goes up, cloud goes down, which is a critical issue for climate feedback. Humidity goes up, cloud goes up. So, well, actually what I would like to do, and I will hope there's someone else here who would love to do it for me because I have too many things on my hands at the moment. We need to go back to the boreal forest. Someone in Canada needs to extract all that data because I only have the PAS. I see signs of memory going back a full calendar year in the boreal forest in these climate data sets. Go back and look at that. We have enough sites, I think. The climate change problem, I was asked to say something about this, so I'll wave my hands and say, we have multi-model ensembles, but still, many of them are not sufficiently validated against real data. only I would have to simplify, I would say the models like the European Centre, which is slowly being moved into the climate domain, the UK Met Office model, where the forecast centre and the climate model are essentially the same model, those are well validated. Many of the others are not. Much more work needs to be done to do that. But the grand climate problem, I work in Vermont and I advise Vermont, is that it's now a matter of politics, a matter of ethics. It's nothing to do with science at this point. We know what to do. It's a huge political problem specifically for this country. We made progress with the Paris Agreement. We agreed to do what we promised to do in 1992, mapped it out a little bit better. We have one global hotspot on this, which is that China is moving aggressively in this direction, and they're doing it for reasons that was never discussed in this country. We just wave our hands at their politics, but they're using a systems engineering approach, which if you just imagine that we had tackled climate change in the United States with a systems engineering approach, instead of what has actually happened, we sold Congress to a bunch of libertarian billionaires who funded the Tea Party. And they got Trump as a candidate, which horrified them as well. And just so you understand, I am part of the fictitious global conspiracy of 10,000 scientists that is making these claims and mapping out what is going to happen to our future. And I really shouldn't do this. However, my warning is, of course, collapse is looming unless we change our strategy here. But on the optimistic note, yes, Fife and Boreas were transformative. Those time series, from the modeling perspective, gave us ground truth for the first time, something to shoot for that enabled the models that lack processes to put them in, calibrate them, recalibrate them, run them, test the results, run them again, and we've gone through several iterations at this point. I have probably the Fife data set was used to test every land surface model for about a decade until the wider FluxNet set came along. Boreas and successor BERMS, many forest models, many snow hydrological models, and the understanding is still being transferred to all our global systems models. Thanks.